Recording.
All right, guys, let's get started. So this week on Monday, last week we were covering linear regression, right? And we kind of introduced logistic regression this week and also jumped into multi-layer perceptrons and basically, neural nets and deep neural nets, right? So I've given that contrast now with all the algorithms. So what remains is to do in NumPy, the logistic regression algorithm, and then after that, the multi-layer perceptron, right? So those are the two things that remain. However, I thought it'd be probably a little bit better. I'll do those, but I'm gonna change the order a bit. And instead, we're gonna jump into TensorFlow today. The reason for that is you've got your project up. I wanna give that to you so you can start playing with it. And then what remains really is just like theory. So even though we're going to go over the multi-layer perceptron algorithm in NumPy, you wouldn't really implement that from scratch, right? You would use the advanced tools. So that way I changed the order a little bit, and that, that will allow me to introduce TensorFlow a little bit sooner. And then you guys now have it and have a couple of weeks to finish up the project. Does that make sense? All right, so we're going to do that today. And then, so the plan is then today, I'm going to open up a Jupyter notebook. And this actually, we're going to do this. I'm going to do this actually on the Python, on the terminal. So the Anaconda prompt actually is what I'm going to use. So I'm going to go to Anaconda and Anaconda prompt. I'm going to share the screen. Okay, so you guys should be seeing this now, which is just on Windows. This is the Anaconda prompt where we're going to be writing our code. I remind you next Tuesday, or Monday, sorry, will be your exam number 2. So it'll be online. So just, you can take it from home, right? And it'll open up on Brightspace at this time from 12 to 2, so don't forget that. The following Wednesday, if I don't finish this TensorFlow thing today, which I probably will, because as I've told you many times before, you already know it, right? You just, because, if you understood the ideas of the perceptron even in linear regression and NumPy, you kind of have a gist for it, right? The basic template. But today I'll go over TensorFlow. So what's different here is that we still can use NumPy for various things, but now we definitely need to use a library, a specific library that was created by Google. It was released in 2015. Okay, so what's that? 6 years now, 7 years, and they're actually up to TensorFlow 2 now. So it started with TensorFlow 1. I really like TensorFlow 1. I'm one of those people that was really sad that they replaced TensorFlow 1, probably because it took me 3 years to understand it. And then they made a major revision, and now I don't understand TensorFlow. It's not intuitive for me. So I switched to Pytorch, which Pytorch is more intuitive now. I wish I had just started with Pytorch in the beginning, right? But that's how it is. Anyway, so what happened in the history of TensorFlow is that, as everything, right? Google was doing this in-house probably in 2014. They developed this. They decided to release it to the public. They did at the end in December, I think, of 2015. So it was almost like 2016 that it became available. Before that time, you literally had to code this in C++, and you had to do all the parallel computing yourself, or the parallel programming with a library called CUDA for NVIDIA, and that is not easy. I mean, I remember I was working on that in 14, and I was trying to implement KNN. If you remember KNN, that very first really easy algorithm, it was not trivial. And that was just because of the parallel computing. So definitely this, changed the game for sure. And then Facebook came up with Pytorch as their own in-house thing. And I really like Pytorch, but it's a little bit different. And they're the same. I mean, it is what it is. So TensorFlow came out December 2015. It was good. And then in 2020, I think the year of the pandemic, actually, when was that, 2019? Yeah, so around there in that summer, they released TensorFlow 2. Okay, and TensorFlow 2 is better, sure, but it was a major revision, right? Now, a lot of people didn't like TensorFlow 1. I just like the fact that you can like lay out all the like matrix multiplications really nice. I really like that, like NumPy. But a lot of people didn't like that. So a thing came up called Keras. And Keras is like a submodule within TensorFlow. But it was a separate thing. It was just some person who said, I hate TensorFlow 1. I'm going to create my own thing. They created Keras. Keras became very popular, where people didn't want to use TensorFlow 1. They just used Keras. TensorFlow 2 then just made an arrangement where now Keras is built in. So, and yes, Keras is easier. I agree. So for a lot of the things that you want to do, you probably want to use Keras. Certainly for ITS 365, we're going to use Keras because it is easier than, say, TensorFlow 2, right? So just be aware, I'm not teaching in this class TensorFlow 1. I'm not teaching TensorFlow 2. We're only looking at Keras, which is a TensorFlow submodule, but it's easier. So that's what we will explore it. But at the same time, me giving you that already gives you a lot of power to do a lot of things, okay? So you guys will be, and that's how it is. It's all libraries. So if you guys ever take 530 with a transfer learning class, you use Pytorch, but there you have other modules like Fast AI, and Fast AI just simplifies like Keras even more. You know what I mean? And it does a lot of other things. You have now thousands of pre-trained models that you can use for your problems. And so you don't actually have to do the training that you're doing right now, right? From scratch. In any case, so that is the plan. So that's the story. So you're going to be learning Keras. So why is this relevant? So TensorFlow is built so that you can handle big data. So before, you were kind of limited to data sets of 100,000 by 10,000. That's kind of where the limit is when you have 8 gigs of RAM. But now TensorFlow can handle millions of records, right? It's very efficient in the way that it loads the data. It doesn't load all the data all at once. So it's not going to take 2 million records and like give it all at once. It's designed so that it takes the data in batches, right? So you guys remember those 2 for loops. We had 4 epochs and then 4 sample in data set, where you can grab, instead of just 1 sample, you can grab maybe 64 samples at a time. And that's called a batch. And that's how TensorFlow will do it. So that part might be a little bit slow, but everything else is pretty fast. Okay. So TensorFlow is now designed to be very fast. So remember that Python is an interface to C++, and so is TensorFlow. So TensorFlow has all these libraries already compiled in C++. What you're creating in the Python script is just basically like what is called a computational graph. It's just a representation of things. And then the library just grabs that and feeds it into the C code. You guys see that, the binaries. And then the binaries run super efficient, right? And perform matrix multiplications and everything. Keras is now pretty robust that it runs on Windows, Mac, and Linux. It used to be that, first Linux and then Mac and eventually Windows, but now it runs pretty well on Windows. So that's the plan. So I think that's all I have to say really about it. So now you have a tool, one of the 2 tools for big data. And believe me, when you say you can use Keras, that's what a lot of people will say. So. And then you just get into like these clubs, right? So think of it like, what do you call it? Like fraternities or like in the East Coast. Oh, what high school did you go to? That kind of thing, right? So basically it's just, oh no, I'm a Pytorch. I'm a TensorFlow. I became angry with Google when they changed Tensor to TensorFlow. I've always been a very big critic of what they did. Anyway, that's the story. So now let's start with what I have here. I have a simple deep learning algorithm with TensorFlow. Okay, so we're going to take a look at this one. So we're going to use the Anaconda prompt for this. So this code is already on the GitHub if you want to use that. Okay. So, you know, when you installed on Windows, your Anaconda environment, right? You have all of these features. So all you have, am I recording this? I'm recording, audio's on. Okay. So when you installed on your Windows machine, Anaconda, right? You have a prompt. So all you have to do is you click on the icon here and you go to the Anaconda option. And then you go over here and you pick Anaconda prompt. Okay, so just make sure you do that. You could also use a Jupyter notebook, but we're just not doing that today. So now I'm here and I want to find my ways. So I'm going to go to where the scripts are. Okay. And I'm just going to navigate to ITS 365. ITS 365. Yep, 2022. And then, so this is where we've been writing our scripts for this one. So I'm going to create a script here, right? And then we're going to, you know, we're going to run it. Okay. So I'm going to open up the folder system. And I'm going to go to the desktop and I'm going to go to this here. And yeah, I'm going to go to 2022, I guess. And then I'm going to create here a text file. And let's call this one simple deep learning. So remember, we are now, this week, we went from logistic regression. We saw the intuition of that, and immediately we were able to run through logistic regression, multi-layer perceptron, and basically deep learning. Okay. So in fact, what I'm going to do today is I'm going to implement logistic regression, multi-layer perceptron, and a deep neural net. But do you guys see that? So because at the end of the day, what's happening there, if you remember that we have the same loss function, the cross entropy, but what's going to change is the architecture. We add more layers, right? So if we only have an input and an output, what's that called? For classification. What's that called? What's the name of that algorithm? If we don't remember the chart I did on Monday. So if it has only an input layer and an output layer, what's that called? And it predicts classes. Logistic regression. If I put an input layer, one hidden layer, and an output layer, what's it called? Not perceptron, multi-layer perceptron, MLP. If I take one input, one hidden layer plus one or more hidden layers and an output layer, what is that called? Not a neural net. Deep learning. They're all neural nets. You see that? Neural net is just the idea of connecting nodes with links, right? So I can draw 3 nodes and one, like the perceptron, that's a neural net. Linear regression is a neural net, right? You can represent it. It's just, right? But you predict what? Minus infinity to infinity, real valued numbers, right? And the objective is different. You're trying to fit a line, not a line that separates data. With logistic regression, you do, as I said, same as linear regression, except that logistic regression predicts classes, not real value numbers. And once you start adding layers, they're called multi-layer perceptron, or the more layers you have, deep learning. Does that make sense, guys? Does that make sense? Is that clear for everyone? All right, so yeah, so this one we're going to call simple deep learning. Okay, so we've got our script here, so you should all be seeing that the script, or no, maybe. So now we're going to open this with Notepad++. And we're going to start adding the code. Yeah, all right, so I'm going to make sure this is correct. All right, so we're here. What do we need to do? So you probably don't have an Anaconda environment. Okay, so I'm going to give you the commands in the script. So, you know, first of all, use, this is not something you type, right? I'm just saying use Anaconda prompt, which you've seen me, I'm there. Then once in there, you're going to run conda, because you all have Anaconda by now in the semester, right? You've been using the Jupyter notebooks through it. So conda create, and then -n, and then I already have this environment, but you guys will create it. Let's say, so here you can see I'm doing TF stands for Tensorflow underscore V2. That just means you're installing Tensorflow 2. Okay. So that here just means, you know, by default, when you do this conda create, it'll just grab Tensorflow 2. They're actually trying to like deprecate or get rid of Tensorflow 1. Okay, so then after that, we're going to do conda environment list, just to see, you know, what's in the environment. So you've created one, and then after that, you can do conda activate, which basically means that you're going to enable that environment. You've created it, but it's off currently, right? So now you have to turn it on, and basically this takes you to that environment. Okay, and then after that, you're going to install some of the libraries that we're going to need. So here you can do pip install, and you can say Keras, which is the module that we're going to be using specifically. Remember the simplified module for deep learning, but it's built on top of TensorFlow, and then also sklearn, which is always a useful thing to do. Does this make sense? Okay, so you will run this. So I will go ahead. I already have it. So I just need to enable it. Okay, so I'm going to do conda environment list. You can see that here. And it should list out the ones that I have, right? So you can see I believe I've done this in so many semesters that I'm just going to stop, or otherwise I'm going to end up with one for every year, right? So I'm just going to grab one of these, probably the one that says 365. That's probably the one I'm thinking, the one I did last year. So I'm just going to do conda activate, but you guys have to do what I wrote, right? So because you have to install the libraries and probably create the environment. So here I'm just doing conda activate TF v2 365. Right? So I activate the environment. So if you notice, base here, the keyword base has now changed to the word TF-v2 365. So I am now in that environment, and I should be able now to run my code. So if I do dir here, I need to navigate to 2022. And you can see my script is here. Simple deep learning. So this is the one that we're going to be running. So I'm going to do Python. Simple deep learning. Currently, it doesn't do anything, but we can now run it in the appropriate environment with all the appropriate libraries. And as you can see, that should be pretty straightforward, right? Any questions? All right, doesn't sound like there's any questions. So let's go back to the code. And now we need to start thinking about how to write neural nets, which in our definition, a neural net can be the perceptron, linear regression, logistic regression, you know, any higher neural network. Not every, because not decision trees. just the ones that this family that we've been studying after spring break. Well, the correct names are the perceptron, linear regression, logistic regression, multi-layer perceptron, deep learning, deep neural networks. They're just deep because they have more layers, right? For the longest time, people had in their minds, if you could only make this deeper, you know, that kind of became like this thing. They would only make the one hidden layer and couldn't do more just because the computing power, as you know, estimating all those weights is a lot of work. All right, so, well, to do this, we're gonna need our library, and we're gonna introduce our famous Tensorflow library, STF. Oops, just TF. That's it. With this, you now have all the power of Google. Congratulations. Right? Minus the GPUs, of course, and the TPUs, and all the computers they have, and scientists. And well, a lot of knowledge and money, unlimited money. But you have TensorFlow. All right, so import NumPy as NP, right? That one you already know about, and you continue to use it. Pandas, as you have used a little bit this semester, as you know, is extremely useful, but we probably don't need it here. sklearn will be useful as well. And we're going to use something called maybe the TensorFlow. I'm going to at least show you that it exists, the TensorFlow datasets library. So that should be import. This one is great because it's got now more data sets, right, for the specific tasks. So TensorFlow datasets. Okay, so we're going to import TensorFlow datasets as TF DS. Okay, so import TensorFlow datasets as TFDS. All right. We're also going to import from Keras, something that you should be very familiar with right now after the semester, from sklearn.metrics import F1 score, precision score, recall score, confusion matrix. All right, so sklearn metrics, F1 score, precision score, recall score, confusion matrix. So these are the ones, the metrics that we've been using so far. All right. And then finally, to be able to create our neural networks, I'm going to show you how you bring in special constructs that will allow you to build neural networks more easily, right? Later on, usually what I do is I show multi-layer perceptron and I show you how much work it is to build it from scratch. And then that kind of really is to motivate to do this, right? But this time around, I decided to start with this first just to get you guys access to this. And then later on, we're gonna, at the end of the semester, we're gonna go back to the theory. All right, so I'm gonna do here from Keras. So you can see now I'm using Keras itself. So there's from Keras utils, import a function called toCategorical. So these are just utility functions to change values, like the categories, for instance, kind of like what you did in Weka when you did from numeric to nominal, right? So similar ideas. Now I'm going to do from Keras.models. Right? So you can see this is where it gets important. We're going to import probably the most important module for Keras for deep learning, which is the sequential module. Sequential. Okay. And the way that this works is basically that you're going to build a sequence of the neural net from the input layer to the output layer, right? So you need to define all those layers. You use this object to kind of say, okay, this is the thing. And now you just start adding things to it, like a list. And then in order, it'll respect them basically. but that's, you know, how it should be. So that's the sequential module. Then we're going to do from Keras, and we have another construct called layers, which will allow us to define the layers in our neural net. So the most common layer that you're going to use is the dense layer. And what the dense layer means is that all the neurons from one layer are connected to all the neurons of the previous layer, which would make sense, right? Versus you could have not that, right? But the dense does, you know, fully connect it. But there's a few other layers that you could use. So I'm going to introduce a much more advanced layer called the Conv2D. This layer is convolution 2D. This is for like images that are two-dimensional. This is this is one of the most powerful algorithms in deep learning, the convolutional neural network. You've probably heard a lot about it. A lot of problems were solved through this, right? Through this idea. And then you have another layer called a flatten layer to flatten things out. We may or may not use this one. And there are many more. So this is just an example of some of them being called. All right, so that's all the libraries, or should be all the libraries for Keras. Now we can proceed and take a look at, let's just quickly go and kind of explore some of these. So let's explore in particular the data sets objects. So I'm going to use TFDS, TensorFlow dataset, to kind of bring in the iris dataset that you should all be familiar with, right? We're going to bring it into our code. So I'm going to say TFDS dot load, and then from that dataset, I'm just going to bring in iris. All right, so the iris dataset basically. So let's just run this. Let's see if that we have some functionality going. So I'm going to switch over to the prompt, the Anaconda prompt. And I'm going to go ahead and just run the code. It's currently running. All right, so usually you get this output. It says TensorFlow core platform. This TensorFlow binary is optimized with one API deep neural network library, one DNN to use I guess, performance critical operations. To enable them in other operations, rebuild TensorFlow with appropriate compiler flags. So this is, by the way, I'm using default CPU for this. If you want to install for GPU, you have to go to the TensorFlow website and you have to go to installation, and under there you have to go to install TensorFlow GPU. Okay, guys, so it's a little bit more specific. There might be some Anaconda. It may just be as simple as another Anaconda install command as well. Things are changing as we speak, right? So I don't know what it currently is, but usually those are probably go to the installation and then they'll tell you if it's as easy as an Anaconda command or a little bit more involved. One thing that I do find difficult is installing Pytorch and TensorFlow on the same machine, because they both interact with the same GPU. And I don't know, there's like, what do you call it? Drivers, right? So the drivers may be different. And so you have to remove one. And so it's kind of a, but anyway, if you're just using CPU like you're doing here, you know, this should be more than fine. And this will be very powerful, as what all you're doing is right now is learning. Now, keep in mind, the code really does not change. Whether you're writing this for CPU or GPU, that's the beauty of this. And hopefully what you should understand is that, you know, you write your code, right? Doesn't matter if it's CPU, GPU, you write your code, and then you do have to tell it, okay, run this by default on GPU or CPU. Yeah, that's kind of the only thing. Or I think by default, it detects nowadays if you have a GPU, and then if you do, it'll just go with that. But as long as you have the installed software, right? Like I have a GPU box. I already have an Anaconda environment for GPU. So all I have to do is activate it, put in code in there like this, maybe it'll remember It'll say, okay, do I have GPU? Yes, then use that. You guys see that? So that's a good one. All right, so we were able to load the data set. So now let's go ahead and kind of just print it out. And this is just for informational purposes, but so that you know that you have this available. So I'm going to do xtrain iris, and then from iris, which I called it iris, I'm going to bring in the train data. Okay, so that gives me the train data. And we're not going to print the whole thing. Let's just print out the shape. So I'm going to do print xtrain iris.shape. All right, so let's save this and let's run it in the Anaconda prompt. And now we should see the shapes of our X data. Okay. Xtrain shape. Prefetch data set. Huh? No, that should be a built-in TensorFlow. Why is this not working? Okay. Let's just see, I guess, what this object is then. Xtrain iris. All right. All right, so there's the object. It's a dictionary. It's got features, label, types. Okay, so features. Try that. Hmm. I did load, and then all right, let's try converting it to a pandas. I'll do import pandas. Iris. Let's do tfds.load iris, comma, with info. True. Comma split. Okay. This will give us info. So now I'm going to create a data frame equal tfds dot data frame. Iris, comma, info. All right, let's see if this works. I really just need to view it. I mean, we're not even going to use it. Pip install pandas. Okay, try it again. Okay. All right, let me try. Get rid of this. I can just print iris like this. Okay, so it gives us this. This should be pretty easy, but I can't think of how. Yeah, see. So oh, there it is. Okay, so that took a while. All right, so this, we can see now the data in Iris. So we've got 5.1, 3.4, 1.5, 0.2, right? And we've got all of these basically are the samples, which are represented as tensors, okay? So you can see that the TF-DS loads basically reads in the Iris data set. And then I had to iterate through it just to kind of extract it. I'm sure there's an easier way of doing that. So we're able to see the data. We're actually not even going to use this right away, but we were able to view the data there. And we can go back to the Anaconda prompt, and you can see here examples of it. You can see that they're basically represented as tensors. Let's go ahead and continue. So now we're going to initialize, basically, since we're using neural nets. So if you remember on the discussion on Monday, right, we talked about that mountain range, and we talked about how there was a giant walking on that mountain range, and we said you do that multiple times and you start at multiple places, right? So you start at multiple places. So that means that TensorFlow, by definition, tries to have a lot of randomness built into it. Okay, and the idea with that randomness is that simply, you know, you wanna start things a little bit random. You initialize the parameters randomly and so on. So usually there's a way to control randomness by just setting up random. So this is for the TensorFlow library. So TensorFlow.random set seed, and you can just put in any parameter you want in here. So just plug in 1. I'm going to repeat the same for NumPy. I'm going to do np random dot seed, and that's also going to be a 1. Okay. So then you have that. All right. So we've defined just a couple of examples here. Now we can, let's see. We're going to initialize some data. Okay, so we're going to create some data here. So let's do X and Y. Right, so this is your X data and your Y data. So I'm just going to do numpy.random. This is a NumPy. Now, one thing that's really important is that TensorFlow has TensorFlow tensors, and NumPy has NumPy arrays, right, which are tensors too. But the data type, they're very similar. But the data types are specific. So one is for TensorFlow, one is for NumPy. You kind of sometimes have to switch between the two of them. That's what I was trying to do. So one of the errors, you know, you saw they were tensors. That starts. So if you saw my intuition, I grabbed the thing and I did dot shape, right? What I expected in NumPy. Then that didn't work. So I said, okay, it's a tensor. I need to make it into a NumPy. So I did 2 NumPy. That didn't work because it was dot NumPy. But then the data structure also still didn't work because it was a much more bigger data structure, right? And I had to do the for loop to kind of break it down into the individual tensors, which then I could print out. And so that issue that you saw is an issue that you're going to have to deal with, unfortunately, right? And NumPy, that's why NumPy is so great, right? NumPy is like the gold standard. And then Pytorch and TensorFlow over time have tried to be more like NumPy. I almost wish they had just started with NumPy and built, but because they all want to build their own thing, right? And so eventually there might be a NumPy that competes with them. There's a language called JAX, I believe, right now, that is kind of the NumPy version of it. So I can definitely see NumPy competing with them if they have the resources. But right now, the problem I was having is this thing of formats, right? From TensorFlow to Pytorch to NumPy, they're all tensors, but in their own specific. Look at this. TF random dot set seed NP random set. You see how they're inconsistent? And this happens a lot. So when you're trying to remember a function, you always remember the NumPy one and the TensorFlow is different. You see that? So unfortunately, these are issues that happen. Is just, you know, the idiosyncrasies of the people that develop. All right. So, but anyway, so now we do, I'm creating a data set. This is going to have a random uniform distribution. So notice that I am no longer initializing things to zeros or things like that, right? So I'm just going to create a random uniform where the value is going to be, the low is going to be 1 or minus 1. Minus 1. And the high is going to be 1. And then I have a size equal 200 by 2. So it'll have 2 features and it'll have 200 samples. Okay. So I'm creating basically a data set here to use instead of using this iris data set that I have here. Okay. So the options are read in this iris data set, create your own data set, or what you will actually do, which is something you've been doing all semester, reading your data from a CSV, loading it into memory, and then putting it in the format of TensorFlow. So if you follow this code, probably the best suggestion is convert it into a NumPy array first. You guys see that? Because this is a NumPy array. And this is very important. Otherwise, you're making your life very hard. You guys understand this? I mean, you saw that I had a hard 5 minutes just a while ago, right? Because of that formatting. And so just make sure, pay attention to this issue of, you know, because you'll probably want to read with pandas or something, but convert it to NumPy so that it picks up from here. And then the function that I used to convert it into a TensorFlow tensor works out of the box. Does that make sense? Lenny, am I going to get the thumbs up? All right.
My question is, why does it need to go from NumPy to TensorFlow and it can't go Pandas?
It could. I'm not saying that it can. The code that I have here starts at NumPy.
Okay.
You see this?
Yeah.
So probably what's going to happen from here is I'm going to switch it to a TensorFlow tensor or something along those lines. All I'm saying is if you want to make your life easier, you would make it consistent with this. However, you could, I'm sure, figure out a way to do it. Yeah, it's up to you. Yeah. All right, so now I'm going to do the y, and the y is going to be np.ones. np.ones. Okay. Why is this ones? This is going to be the labels. The length of this is going to be the length of x. So for right now, this y is all ones. That's not good, right? We need to have what? 2 classes at least, right? So like a binary problem. So we'll look at some data sets here. But for now, this is all ones. Now, what we're going to do is we need to make this into different labels. So you could just randomly assign some of these to be zeros, and that's fine. We could try other approaches. All right, so we'll need to come back to this in a sec and think about what we want to do. But for now, we kind of have the tensors or the NumPy arrays in their specific sizes, and we're ready for the next step. So let's go ahead and do this. All right, so now let's print out the shapes. So I'm going to do y.shape. Notice that I'm now doing y.shape, which should work because these are NumPy, and it's what we've been using all semester. This is going to be x.shape. Parentheses. So I'm going to go ahead now, save it, run it. Oh, and it's still printing. I don't want to print this anymore. No, I commented that. Let's go ahead and run that. All right, and I've got 200 samples, and then that's the y, and then I have 200 by 2, that is the x. I can also print the data just by removing the shape. Okay, so I'm going to save this one. And there it is. That's the data that I just generated. Okay, so this is for your term project. Obviously, you're bringing in data. Like I'm picking on you because I remember your project, the Titanic, right? So you're doing that, right? Yeah. So this would be, his Titanic data, and then he would have labels. Now, notice all my labels are 1 currently. So we need to change those to be 0 as well. We could do it randomly because we just care about the pipeline, really. But we'll think of something else. Does this make sense, guys, so far? All right. So let's go ahead then. Now we have some data. Now we need to, again, because this is supervised learning, right? We need train and test data, right? So I'm going to slice out, because I'm using NumPy, so pretty easy. So if you found, so the great thing about using TensorFlow, for instance, is that if you found NumPy to be hard at the beginning of the semester when you had to do all those problems, now you'll want to go back to NumPy, and now you'll have a fonder feeling towards NumPy because you'll see that this is a little less, Google is a little bit more, just a little bit more advanced. I don't know. All right, so let's go ahead and create the 2 sets. So I'm going to do X train, and I'm going to do Y train, right? So just like the same thing we've been doing all semester. As you can see, it's pretty consistent, right? And that's why I keep saying today, you already know like 70% to 80% of this code. And then I'm also going to do X test. And I'm going to do Y test. So here, it's going to be equal sign. And I've got X. I'm going to use all the samples from the beginning until 100, since we have 200 of them. And it's going to be all the columns, right? That's slicing, as you have learned by now. And then we're going to do the same with Y. So Y is going to be the same, first 100. And basically, we just have 1 column in there, so we don't need a comma. For X test, I'm going to do X. But now the other 100, right? So I'm going to go from 100 to the end, comma, all columns. And then for Y, I'm going to do from 100 to oh yeah, no, that's correct. Yeah, from 100 to the end, right? So now I should have my data sliced correctly. All right. So now I've taken care of the data, and if you notice, since spring break, we've been working on code for the perceptron, code for linear regression, and then this week we saw that basically they're all extensions of each other. So now we're going to kind of repeat the same exercise, but we're going to repeat it in TensorFlow itself. So that means just like we were creating neural networks in NumPy, now we're going to specifically create them in TensorFlow. So the first one I'm going to do is the logistic regression. So this is important, guys, that you understand these differences, because the exam questions are going to be exactly about this, right? Remember, your exam is Monday. No class meeting. You can take it home. It'll open up from 12 to 2 on Brightspace. So make sure to remember that. But it's very important that you understand that logistic regression, right? So these are the algorithms, you know, what are the differences? So I'm going to do logistic regression, multi-layer perceptron, multi-layer perceptron, deep neural network. So those are usually referred to as DNNs. But now you have to specify how many hidden layers. So the architecture. So in this case, I'm going to say deep neural network with 3 hidden layers. So imagine training this in Weka. Remember, you just did the MLP with 1 hidden layer. Now imagine adding 2 more, right? So that would be, but TensorFlow now will do this very efficiently for us. You guys see that? Okay, and that's it. All right, so that's the plan of what we're going to do. So let's start with the first one. And remember, our data is still not perfect because we have only labels of one and not labels of the other class, but we'll work on that in a sec. Let's just focus on the first algorithm. So logistic regression. Who can list the layers associated with logistic regression? What are the layers? The layers of logistic regression. Input, output, they all have output, and then what else? Nothing else. Well, not ones and zeros, just inputs and outputs, right? And no hidden layers. That's the key thing to remember, right? So I'm gonna write here, no hidden layers, only inputs and outputs. All right, so let's go ahead and define our model. So I'm gonna do model. You usually name the object model, and then you're gonna say tf.keras.sequential. Right? This implies that you're building a sequence of layers. It's going to start with the input, end with the output, and in between all the layers that you want. Okay, that's it. It is literally that simple. So I'm doing here sequential. So that's the object. I just created it. So now I'm going to go over here, and now we start adding the layers to the model. That's it. So I'm going to do model add, and then here you can take a notation like you do in jQuery, etc., just kind of like this to make it nice and neat. All right, and so now we start adding layers. Okay, so in this example, I'm going to add tf.keras.layers.dense. Remember that one? So I'm going to use the dense layer, and now I'm going to specify what goes in here. So this layer takes So this layer takes units, which is the output, right? The output, so in this case, 1, okay, comma, input shape, which is the size of the inputs, which is going to be just 2, comma, so that's how you write it. And then you specify the activation function. We talked about activation functions on Monday, right? What was the activation function of a logistic regression algorithm usually? You guys remember? No? Sigmoid. Okay, it's the sigmoid. So let me actually get my tablet for this. All right, so if you look, what's important here is we've got this 1 and we've got this 2, right? So what does this neural network look like? This neural network actually looks like that's the 2 and that's the 1. There's an activation called a sigmoid. What does that activation do? It's got the S shape, right? Between 0 and 1. You remember that? To create the mapping to probabilities. That's the network we just created. Like literally, we just created this network, okay? With the code, but you know, we don't draw them, we write the code like this. Okay, so this is a logistic regression algorithm. So now let's go ahead and do a model summary. So notice that's it. That's, you know, there you go. Logistic regression is done. And now let's do a model summary. Okay, so I'm going to save this one. We still need to add a couple more things, but let's just run this. Oh, missing that. All right. All right, it worked. What do you guys see here? So the input, it shows you the layer. It says it's a dense layer, right? The output shape is 1, and it says there are 3 parameters that you need to calculate. What are these parameters that it speaks of? Who can tell me? What would these 3 parameters be? Nice. All right, very good job, Lenny. So exactly right. So W1, W2 plus the bias. That's the 3 parameters. Very good. All right, and this is nice because you quickly start to see how this jumps exponentially, right? This could be done in the 1940s, but up until the 80s, there was a limit to how many parameters, right? Or the 90s. So very good. So now let's go back to this and let's go back to the code. So after model summary, now we need to specify a few more things for this model. So we're going to say model dot compile. And again, you know, we can use the syntax tf.keras.layers. Okay, so layers. Oh, sorry, not layers. Sorry. in compile, we specify the optimizer. All right. So basically, all we have to say is what optimizer we're using. So in this case, we're using stochastic gradient descent, right? So that search algorithm that pretty much you always use. But we specify it. You might say, why specify it if we're using that one? Because there are several variants of it. There's one called the atom optimizer, which is still stochastic gradient descent, but with adjustment. So you get into the habit of specifying these. Optimizer is going to be tf.keras.optimizers dot stochastic gradient descent, okay, comma. Then if you remember, we have to specify the loss function. What was the name of the loss function that I said we use for logistic, multi-layer perceptron, and deep neural networks? I gave you that. What was the name of that loss function? Exam type questions. Nobody remembers? Cross entropy. Right, we went over that on Monday. So in particular, because this is a two-class problem, keep this in mind. Like, this is important in your data set. If you have more than two classes, you cannot use binary cross entropy. You will have to use a multi-class cross entropy. There's two variants of it. Okay, so just be aware of that. But this one is going to be for two-class problems. So it's going to be binary cross entropy. And metrics here, it's going to be the metrics that we want to use. So for this simple example, let's just use binary accuracy. So I'm going to do tf.keras. Notice that you feed it as a list. That way you can have more than one metric. So in this case, tf keras metrics dot binary accuracy. Okay. Binary accuracy, and that's in with parentheses. Okay. And finally, we're going to do the model fitting. So everything that I was doing before, remember what we did? We do the for loop and the fit function, and it would give us the weights and all that. You guys remember that? Here, we just kind of do it this way to make our lives easier, right? So now the model basically also has a built-in function called fit. So I'm going to say fit. This returns a value. So we're going to call it history or whatever you want to call it. And then we're going to do model fit. And again, you need to specify some parameters. So here we need to say the X train data set, right? Comma, the Y train data set. To see the performance, you can also, it has a built-in parameter called validation data. And what that means is you give it the test set and it's going to give you the performance of the model, you know, without you having to write a whole bunch of for loops or anything like that. So here you do validation data. So you can see how this is a lot easier. This is X test, comma, Y test. You also specify how many epochs you're going to do. So number of epochs. So in this case, that would be 200. You're also going to specify the batch size, which is going to be batches of 2. So that just means you're just going to grab 2 samples at a time. If this was really large and you have a GPU, then the batch sizes can be incremented. But you need a lot of RAM for that to work. All right, and then verbose just means that it's going to print out some statistics or data as it's doing the work. Verbose. Got it? All right, so we should have a working pipeline, except that our labels are all ones. So the results might be a little bit, you know, messed up, but this is it as far as setting up a neural net with Keras. Does it make sense? Any questions? No questions for anyone? All right, so let's save it and let's try it. right, so let's let it think for a while. All right, there it goes. You see that? It's learning. Look at the loss function. Do you see this value going down? That's good. That's what we want. It means the error is going down, basically. Okay? And then that's it. So the accuracy here was, well, 1 because it only learned 1 class. Got it? Let's now go back to our code and let's just modify the labels a little bit here. Where was that? After here. So let's change the labels, and I'm just going to do something to change some of them to zeros, okay? You don't really have to worry about that because you'll be bringing your, this is just randomly generated data, but at least we'll have zeros and ones here. So we're going to say X for all samples 0. This is just going to return true when you meet this condition times X all samples 1 0. Okay, so that this is basically the XOR data set, or it should be the XOR data set now. So I'm going to put an input here so we can look at the data before I let it run. All right, so now let's save it. Okay, as you can see, what's important here, look at the labels. Now there are zeros and ones in this data. Do you see that? And this is supposed to be now the XOR data set, which is a hard problem to solve without neural nets. Okay, so let's let it, now it goes, it's training, right? Look at the loss. The accuracy, you can see it's going up. That's a good sign. Is it not going up? Not going up. Oh, it's not. Actually, what happened? Interpret the results, please. What's the final loss? 0.68. What about the accuracy? On the validation set in particular. On the validation, remember, validation is the one the data doesn't train on. It's 67, right? You see that 71? So what that means is that's the accuracy, 71. 71% of the time it got it right. But 29% of the time it got it wrong. Why? What does logistic regression try to do? No, separate. But it looks like this. It looks like this, right? Intuitively remember. Is there a line that separates this data perfectly? No, right? We need some approximation that creates something like that. You see that? This is where neural nets should solve this problem, right? So we have right now an example where we tried logistic regression and it just didn't work, right? Or it didn't work very well with our algorithm. So now let's try another one. Let's try the multi-layer perceptron, right? We don't have to type all of it now because we already typed a lot of it, right? So I can just go ahead and I'm gonna, in the interest of time, I'm gonna jump ahead to a deep neural net, okay? And then you'll see that you can build. So I'm going to jump to this part here. So I'm just going to copy all of this. Copy all of that down here. I'm going to comment out this one because I don't want to wait. And now I'm here. So now I'm going to do, this is going to be a DNN. This is your first deep neural network. So today is a special day, right? You've gone from mere mortals to people that can do deep neural networks, right? So now you can do model, TF, Keras, sequential, right? That's the same thing. We're going to still use the summary. We still have the compile function, and we'll have the fit function. All of that should be the same. But what needs to change now is the architecture. So you're going to do now model add. And now I'm going to do it a little bit differently. I'm going to just move this one up here. And I'm going to do this like that. You see that? And this will allow me now to create more layers. Look at what I'm going to do. This needs to have more layers. All I have to do is copy this layer. And I added my layers. Do you see that? I have to tweak them a little bit, but now I've done it. That's deep learning right there. Just added 4 layers, right? And now I just need to tweak them to represent the thing that I want. Before I just had 1, now I have 4. So I'm going to do model add TF Keras layers dense. Now I'm going to say not 1 because 1 was just the last one, right? So really, I should start at the end, right? So let's start at the end. Model add the last one here. TF Keras layers dense 1. That's the last output layer. Then what is the here? There is no input shape or input parameter except in the very first one, right? So I'm going to get rid of these. I don't need that. Don't need that, but I do need it at the beginning. The first one does need to have one. So dense is this. A function activation could be softmax, but in this case, we also can continue to use sigmoid, right? Remember, we just predict probabilities. Let's go to the first layer. The first layer has the input shape, which is 2, 1. That's correct. The activation function is no longer sigmoid. Instead, what's the name of the activation function that I said we use for neural nets on Monday? ReLU, very good. ReLU, exactly. All right. Now, for the other ones, I'm also going to be using ReLU. And we're almost done, except we need to define the architecture. Okay, so let's do this. I'm going to go in here to the whiteboard. And if you remember, we did this for the first one, for the logistic regression. Now, let's do the diagram for this deep neural net. So it's going to be, the input is still 2. We already defined that as 2. The output is still 1 neuron. We already defined that. But we have how many neurons in between, or how many layers? 3, right? And we're going to define them to have 4 neurons each. Why 4 neurons? Why not? Right? This is your term project. Play with this. In general, you should have a funnel type of a shape, right? Where it's more at the beginning, fewer at the end. But a lot of your projects should be experimenting with these architectures. You see that? See which one works best. There is no formula, except maybe for this funnel recommendation. So now your neural net looks like this, right? And then all are connected because they're dense. So I'm not making all the connections, obviously. But that's the architecture. Input, output, hidden 1, hidden 2, hidden 3, where you have 2 neurons, 4 neurons, 4 neurons, 4 neurons, 1. This architecture of your neural network is what I'm writing in the code here. And so that's why it looks like this. So 1 is the last one. 1 is the last one. The input shape is 2. And then these are the 3 hidden layers. So this value should be what? This is the first. H1 is this one, 4. H2, 4. H3, 4. Make sense? That's it. And then remember the activation functions are ReLU, 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 and sigmoid. So if you remember the lecture on Monday, what this meant was we had to run all of these through the activation function. So here, change color. GALU, I literally learned about it on Sunday, so I don't. You can try it, Lenny, for sure. Try it on your project, and I'll expect to see results.
I don't know if I can do it. I was just asking if people.
No, try it. Try it on the Titanic data. I'd be interested to see if it's better with the GALU over the ReLU. That's your work is that. I hope that makes sense. That's your project. A lot of this stuff is actually easy, as you've seen. It's always about get the data, put it in the format. That's the painful thing. And then the algorithms are actually pretty well established. But you play with the parameters. So all of these are ReLUs. And then just remember this last one is sigmoid. Okay. So ReLU, 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 sigmoid. Okay. So now let's go ahead and get back to the code. So the architecture, believe it or not, is finished. You have the input, 2 neurons, first hidden layer, 4 neurons, second layer, 4 neurons, third layer, 4 neurons, final layer, 1 neuron, all ReLUs, and then 1 sigmoid. This is how you do a deep learning algorithm. Okay, so I ask you this question. Make it 5 hidden layers. What would you do? Where would you add? You need to add 2 more, right? Because you have 3 currently. Where would you add them? Here?
Yeah.
Yes.
You change them to 5, right? Is that 4?
Well, no, I just said add 2 more layers. How many neurons you have in there is it's up to you.
Right.
But you should follow the funnel shape. What that means is what I should have done is 6, 4, 2, or 8, 7, 5, reducing them. Force it to learn with less in general. But, for this problem, it doesn't matter. Got it? That's it. See how easy it is? Created logistic, and now I've created a deep neural net. Done. So if I go over here, I have summary over here. I look at the compiler. Stochastic gradient descent is still there. Binary cross entropy is still there. I'm still using accuracy. Model fit, I'm still X train, Y train, validation set, number of epochs, batch size. It's all the same. That's it. Now the big question is, now remember, the only thing that is really important is if you guys have multiple classes in your data set, it wouldn't be binary cross entropy. You have to look for the multi-class cross entropy. Now let's run it again, right? So we're going to run the algorithm. Remember, our accuracy was 71%. You're at a contest or a competition. Somebody brought in this technique. They got 71%. They have a big prize here for you, a new Mac, but you have to beat this number. Well, you proposed your architecture, and here we go. Oh, it's got the input. Forgot to remove that one. What do you guys see? Improvement, right? You see that? The accuracy is going up. 97%. You won. You get the Mac, right? You see what I'm saying? Because if you think about it, the loss went down. Notice how it was at 65, right? For the binary, for the what is it? The XOR problem, right? The XOR data set that I showed you, it wasn't coming down from 65, but now it is at 0.02, which means the loss really went down. And in particular, look at the validation loss and look at the validation accuracy. This is the most important because it's trained on the data, right? But it's not trained on this validation set. So this tells you how well it's performing, and you were able to achieve an accuracy of 94%. What that translates is that if we go back to the whiteboard, you were able now, whereas logistic regression before could only do this, right? You are now able to do that. You guys understand? As this is our data set, which is called the XOR data set. It's a good data set for seeing how neural nets outperform linear models. Questions? All right, so as a fun exercise for you guys, now create the multi-layer perceptron. So let's go to the code here. So remember, we left that blank. So how would you do it? How many? Yes. So you have this one, right? And then you have this one. Do you agree? Good. Whereas in the other one, we literally only had the one, right? See, this only had one, right? The inputs were 2, the output was 1, right? But now, because we have one hidden layer, we have input, one hidden layer, output, we need to have this one and that one. But that's literally it. You see how easy it is to go from logistic regression to the deepest neural network that you can think of. So it takes almost no effort. So obviously Keras makes a lot of sense for 365. Obviously Keras is a highly abstracted version of TensorFlow. If you did this in the actual this is called what the way that they describe it is the low level API, the high level API. And the high level API is, well, the highest level is Keras because it's got almost total abstraction. The low level API, matrix multiplications, like what we were doing in NumPy. The dot, remember that NP dot? There's going to be a TensorFlow dot map mul. That's the lowest level. But, you know, that's not something. If in the 520 class, the grad level class, we do it in a more lower level. The advantage is it gives you basically a little bit more control. That's it. I mean, as I told you, TensorFlow and deep learning could be covered in one lab. And it's been done. So now all you have to do for your project is play with these architectures, obviously. The inputs are no longer going to be 2. If you have MNIST, right, what would be the value there in input shape if you were using the MNIST data set? That's the number of samples. Huh? 10 is where? So where would 10 go here for MNIST? Yeah, so actually in the final, yeah. So you can create also things like that. So in our case here, because it's binary, remember what I said? We only need 1, but you could have used 2 there as well, which is the kind of the same. for the MNIST, this would be 10. And what about the input here? What would that be for MNIST? What was the size of the images? So 28 by 28, which is 784. But if you just type here 28 by 28, it also understands that because it'll make that operation. Just 784. Got it? Obviously, the hidden layer should probably not be 4, right? What would be the architecture that you would create? Just ballpark. Yeah, exactly. Just keep narrowing it down a little bit. Funnel it. Remember the idea, learn with more, okay? All right, guys, so we'll stop here for today. And I remind you, as I said, exam on Monday, no class, just online, take the exam. Please, it'll be comprehensive. And then we'll be back on, I'll be back on Wednesday for the class, and we will do, please bring questions. Like I would suggest you try to implement this with your project to see if you have issues I can help you with. Otherwise, we're just gonna go back to like NumPy and finishing up the algorithm. So I think we were at logistic regression. We'll go through that. It's almost like the linear regression one, just a little extension, and then we'll do the multi-layer perceptron. And you'll see that it's a lot harder to do it from scratch, but that's just meant to be theory. In reality, when you solve the problems, you should be doing it with this. Got it? Any questions? Yeah, go ahead.
Can we take a moment to look at my
Let me stop the recording here.